Thank you for the introduction. So I will talk about the cohomology of arithmetic groups and integral structures on spaces of automorphic forms. The setup is the following. I basically fix a connected reductive linear algebraic group over Q. So the group always has to be over Q for rationality reasons. If you want to work over F, you just take restriction of scalars. So S in G is the maximal Q-split torus in the center. I also fix infinity of R compact, and so there's throughout the talk there will be a rational representation that I denote like this. Rational means algebraic over some number field or some large enough field Q. And attached to V, we have a sheaf on the locally symmetric spaces of the form xg of level kf, which are just defined as the usual quotients. I mod out the connected component of the R points of the maximal Q-split torus in the center. I mod out k infinity, and I mod out kf, and kf, of course, is a compact open in the finite part. And for some reasons for later, if I denote subscript nod, I understand this as the finite cover you get by taking connected components of the identity here instead of the full group. So attached to V, we get a sheaf, a locally constant sheaf. We denote V tilde on xg kf. And I will start by giving you 3 reasons why we should consider slightly more general objects than this. And one reason is we are usually working with the cohomology of these spaces. That's why these sheaves are interesting, with coefficients in these sheaves. And of course, they have a Hecker action. And this Hecker action is related to the Hecker action on spaces of automorphic forms. That's one of the main motivations why we're interested in those objects. And so 3 reasons why we should consider more general V's. So actually there are more reasons, but they fall into 3 categories. So one reason is conceptual. One class of reasons is that the notion of being cohomological in that sense, so when does an automorphic representation occur in there, if you use this xg and not the xg with the nod, is that in certain cases this causes problems, because the fact that V is rational imposes a certain parity condition at infinity, which is not natural from an automorphic point of view. So we need a notion, or we would like a notion, which is compatible with Langlands notion of L functions, or definition of L functions, and also functoriality, which is of course also related to L. For example, if you start in one of the simplest cases, you take GL2 over Q and you consider a cuspidal automorphic representation occurring in the cohomology of GL2 for the trivial representation V, and you look at the symmetric square transfer, you will find that the symmetric square transfer in GL3 does not occur in any of these spaces. Although it's in some sense cohomological, it's regular algebraic, following the definition of Clausel, but it doesn't occur there. It occurs if you take the knot space. This, I will tell you why this is not a perfect solution. It's a technical solution that works in many cases, but conceptually that's not the most desirable way to solve this. So this is one reason why the class of V is somehow not really natural if you restrict to rational representations. Then there's topological reasons. So by that, this is a bit more subtle. So if you consider the same objects, but not over fields, but you pass, for example, to rings of integers, then especially if you look at the prime at 2, even if your KF is neat, you're potentially missing something. The reason is that there is a natural orbifold which lives above these spaces. So let me write it down, maybe here. I denoted xg, so I'll just write another letter x. To the proper état Lie group read. The following form. So the space of arrows, which I denote G1, is just this quotient. So you take the space as before and you mod out R, like the component of the R points of the central torus, and you mod out KF, but you keep basically KF here. So you keep KF inside here. K infinity. So K infinity is still there. And this guy lives, it has a source and a target map to above this space xg, which is the same quotient, but you mod it out. So you can write this also idealically, then it's a bit, I mean, if you split it up in a Archimedean, non-Archimedean parts, you can split up the action of K infinity. But that means basically that this action of the component group, you somehow see this in the orbifold structure. So this is G0. This is the space of objects. This is the space of arrows. And it turns out that the cohomology of this orbifold, I mean, you have a canonical map in the category of orbifolds, which goes from xgkf to its topological realization. So this is just a topological realization of this orbifold. So let's call it P. Then you have a canonical Lorenz spectral sequence, which looks like this. So it takes, basically, you take the right derived functors, well, the right derived functors are just the cohomology, xg f, and you compose this guy with the right derived functors forward along P here at any sheaf F. This converges to the orbifold cohomology with coefficients in F for any sheaf F on orbifold. So this guy here is exact away from 2. So as long as you work for primes sufficiently large or or over fields of characteristics 0, it doesn't matter. So you see everything. But if you work at 2, suddenly you're missing out something here, potentially, because you don't see the higher objects if you start on the space here, right? Because it turns out the sheaf that you define on the orbifold attached to V is just a push forward along P of the traditional sheaf. So the traditional sheaf is just a push forward of the orbifold. Well, there's some stabilizers coming from KF, but if KF is neat, they disappear. But the stabilizers are related to K infinity. So you have an action of K infinity, and this defines this orbifold structure. It's basically, I will talk about the sheaves later. You will see where the sheaves come from. Then the stabilizers are clear, at least in the sheaves that interest me. Yeah, so one is just a projection, and one is basically taking the action of K infinity into account, translation, and then projecting. Yeah, I forgot to write this here. It should be like this. Yeah. So one is just a projection, the first vector, that's S, and the second one is you apply this guy, and then you go down. So you projection is to that. Yeah, to the left-hand side. So the G0, no, well, you're still passing to the quotient. That's what I meant before. So that's why I suppressed it, because you can see it in here as a space. You can split it off. I mean, yeah, maybe writing it this way is not a good. Oh, there. So the projection occurs if you decompose this guy as something like you need it. So that being said, the point is that this, if for example, if you work over the integers, then the right-hand side sees a little more than just working on this side. There's also there are a few technical reasons. So the technical reasons are, so there's two technical reasons. One is you would like to have something like multiplicity 1, or at least, let's say, multiplicity as low as possible in the degrees where you can achieve it. So that's sort of desirable. And the other one is the following. I will illustrate it by an example. I take G to be the restriction of scalars, F over Q of Ln. N. Being a little more explicit, where F over Q is totally real. And so in this case, you can consider some rational model of K, which is just the restriction of scalars in that same extension of the orthogonal group, like the standard model, the orthogonal group over F. And inside, of course, you have the connected component of the identity, which is just the restriction of scalars of SO2. And so what happens in this case is that the observation is that in the world of algebraic groups, the group of connected components here is just a restriction of scalars of the multiplicative group scheme of order 2. And this is étal outside of 2, but not. This is actually a technical issue. It's an obstacle if you consider rational structures at infinity for automorphic representations, because this is not the right rational structure on the group level that you want to see. So one consequence is that if F is not Q, so then it's not constant, then not every infinity for regular algebraic I for G admits a model over the field of definition of this automorphic representation that has been defined by Clausen. Issue you run into. I'm not saying now, for time reasons, what this exactly means. It is related to, that's why I wrote these groups down. So you can also take the Q, the Lie algebra of the group scheme over Q, and then you get something that you could call a reductive pair over Q, and you can easily define what a Harris-Chandra module, GK module over Q should be. Yes, exactly. That's related to this problem. Yeah, I mean, that's a good remark. Harder, in his book with Varaguram, they try to work always with this knot space, but when they pass to the Levy factors of the parabolic, they have to work with a larger k which is not connected. There's no way around it. So it always occurs at some point that there's a compromise to be done. So Harder also, I mean, Harder started in some sense a very long time ago this idea of Harris-Chandra modules over Q, even over Z half. And since he worked over Q, he didn't encounter that issue. So over Q, you can somehow get away with it because then the group scheme is constant. But once you go further, you're definitely running into issues. And on the level of sheaves, it's also more natural, you will see. So you should also replace that notion of GK module, rational GK modules, by a suitable other notion. So the solution that I propose is the notion of locally algebraic representation. And you have to introduce then also locally algebraic notions of GK modules and the sheaves and the like. But this actually has some interesting and nice side effects. So this problem somehow gets serious also, especially when you try to lift this to integral structures. And this becomes even more serious, this problem. That's basically how I encountered this issue. So what is a locally algebraic representation? So the definition is rather easy. So a locally algebraic representation is a triple, where this is a rational representation as before, but you add an action of the component group, so rho pi naught, action of pi naught k infinity, B, which commutes with the rational action. So with you should actually, for technical reasons, consider this as a constant group scheme. And later, because we want to consider scheme theoretic actions if we work over rings, and then this is a scheme theoretic action. So in some sense, what you're doing is you're looking not at representations of G, but G times this constant group scheme. You look at representations of this group. So in Harder's work, Harder takes care of this character. He keeps this always after passing to the cohomology of that space. This group acts. So he sees this action, but conceptually, I would advocate for putting this action first into the sheaf, because then it's somehow canonically defined on all levels. And you will see some interesting outcomes of this. So you get a natural category of rational representations, local algebraic representations, which are sort of augmented rational representations. And these representations, they can be defined over any field and also over rings. It does make sense. And so if we have such a locally algebraic representation, so we start with this object, what can we do? So first of all, we can associate to it a complexification, which is like C tensor. Let's assume we have fixed an embedding. Otherwise, of course, you will have this for every embedding. Original space plus the diagonal. G of R action. So G of R acts, of course, via the rational representation structure, but it also acts via the identification of the component group with this group. So it acts diagonally. And this is the action you want to take. So here you already see more objects than if you just consider rational representations. So you see this twisting of this character here. And then going from here, of course, you can pass to ESI infinity modules. And this is, of course, a pretty faithful functor on that level. Here, well, yeah, it's not essentially surjective. So, and also going from here, you get a sheaf tilde on this orbifold, which is just given by equivariant sections, which you can encode in this action of the group K infinity on that thing, because you basically said how this acts via this representation that you have. And then you guys also get a sheaf E star V tilde KF, which I also often denote just by V tilde. From the context, it should be clear which sheaf it is. And of course, from here you go to cohomology. You get something like the cohomology with supports of your preferred choice on that orbifold, also on that topological space, depending on your desires. Here you have the canonical Hecke action before, because I mean the Hecke action is well defined. That's no problem. And then going from here, there's another way to go. So you have something that's called a locally algebraic decay modules. So this lives somehow in between. So you don't pass to C. This can be done over E. This is basically just a traditional decay module over E plus an action of the component group. And from here, of course, you also have a complexification functor. This is over C. Similar to this one by acting diagonally. So you let K infinity act diagonally. And if you do that business, you actually realize that down here, you have the traditional relative Lie algebra cohomology. Or taken into account with coefficients in VC. And this, of course, is related to when does a complex representation of the complex numbers occur in here. And you also have an algebraic variant of this going from here. So you have the corresponding functor for E. I just make index E here to emphasize this. E, K infinity E. And I should actually put now here S. I take the Lie algebra of S over E, and I add a K infinity E here with coefficients VE, where V is a locally algebraic representation now. So this is not defined for all locally algebraic decay modules. It can be only defined for those where the action at this pi naught action is compatible. Because this is algebraic, so this is intertwining through things, but you can go down here, and then the whole picture makes sense. So, are there questions so far? Okay, so maybe I continue here first. So having this notion of local algebraic representation, having this picture in mind, and this basically gives you another notion to think of, or another slightly modified point of view, how to think of cohomological automorphic representations. One thing that happens here is because you're taking these invariants that Hara does into the sheaf, you actually recover multiplicity 1 for GLN, for example, in bottom and top degrees. So basically, once you fix your sign at infinity, you can show that in characteristic 0, this is a line in bottom and top degree. So you don't get multiplicity 2 for GL2, for example, but multiplicity 1. The multiplicity 2 is related to the fact that you have two choices of signs, so you have two different sheaves, which give rise to two different periods. So this leads to the notion of what I call cohomological types. Which parameterize automorphic periods that you can attach to automorphic representations in a base point free way. So what's a cohomological type? So before I say that, I need to say what a locally algebraic cohomologically induced standard module is. And for that, well, I need to fix Q is the beta stable parabolic. A Levy decomposition like this, where L is defined over R. So there's a canonical definition of actually even a real Lie group L attached to L. I consider modules which come from the complex conjugate of U, which is the opposite, with coefficients in VC, where VC is locally algebraic. So this is a character. I mean, if you're working, if this is a Borel, then this is a character. And I consider the standard, like you have the cohomologically induced standard modules or standard modules. Q lambda, which is just right-derived Ackermann functor in the correct degree that I will not write down. Using from Q to GC infinity, and you apply this lambda twisted by the top U mod U bar. So this is over C. Okay, but like already here, since we allow for locally algebraic representations, we get more representations at infinity than if you start with a rational representation. For example, for GL2n plus 1, so for the odd GLNs, you really get different representations for different parities. Yeah. Exactly. Yes, exactly. That's my definition. I need some way to distinguish these modules from general GK modules. I mean, and those can be defined over smaller fields, but that's not really relevant at this point, except that we know that these models exist. What did I want to say? Yes, and then I can define what is a weight of such a module. So basically, if I consider this construction this way with this character here, then I call basically V the weight. So basically V is the weight of Q lambda, which is a little tricky the way I define it, because the way it's written is this is the module over C. It could have different weights, but if I consider this as a proper locally algebraic module, there's a unique weight. So I consider this sometimes also as a locally algebraic module, and then the weight is well defined. So basically, the weight means the lambda is constructed using the same character at infinity, the same pi naught infinity action that comes from here. You have the same pi naught infinity action on AQ than you have on V. This is the compatibility that you need, and of course, the infinitesimal characters should agree. And then you also have a notion of tempered objects, of course, if this is a Borel, and similar thing. So using this, we can define a cohomological type. Cohomological type. G is an equivalence class. Here's isomorphism classes. Here's where pairs xv, where x, that's why I introduced this notion, is a homologically induced standard module of weight v. So v is a locally algebraic representation. And I have to say what isomorphic means. So xv is isomorphic to x prime b prime if and only if they are isomorphic individually. So which means x is isomorphic to b prime. And I identify them, so isomorphism classes are in relation to each other if and only if xc is isomorphic to xc prime by classical GCK infinity module. What happens here is that this functor going from locally algebraic GK modules to complex classical GK modules is not faithful. There may be several objects mapping to the same, which looks like a defect actually. Allows you to make this into a non-trivial definition. So there may be several elements in the same in one equivalence class which defines a cohomological type. So if, let's say, let's make an example. So I start with G again as before, but now I take GLN, F totally real. And I assume that pi hospital regular algebraic of say weight V, which means it occurs in some of these cohomology spaces for V. You can take it as rational, that's no problem. Well, actually, in some sense is, because if you take it rational, you don't see everything. This V shows up later, so you don't need this V in this assumption here. Then you can define the cohomological type pi to be the equivalence class of basically x v's, where xc is isomorphic to pi infinity and its underlying GK module. That's a very easy definition. But to make this example meaningful, I tell you what happens. In this example, what do we see? I think the orbifold, I erased it. Yeah. Now, yeah. So the remark before, so the G0 I defined for the orbifold is the incorrect one. You have to take the same on the left-hand side as before, is what the remark from the audience. So I thought I could save the notation by taking it as xg, but that's not entirely correct. Anyhow. So what happens in this case? So in this case, there's two cases. So the cohomological type of such a pi is either in a canonical bijection, so a certain torsors. So this is not canonical. So the bijection is not canonical, it's base point free. You need to choose a base point. And that's also why this cohomological type business is somehow conceptually preferable, in my opinion, is that either you get the set of all characters and to infinity p cross if 2 divides n, or it's just a singleton. This is what you see. So here you see the 2 to the power degree of f over q periods in the even case, and in the odd case, you have a canonical choice where you're a canonical sign which comes with the automorphic representation, realizing it in cohomology. So this basically suggests, I mean, this map from here to here is easy once you choose a base point, but the periods, they are in a canonical way numbered by the left-hand side. Because for each element here, so let's take some element inside here, which is the form, isomorphism class of this form, you actually have that in the bottom degree, homology here of this v tilde as a to the component pi f. So this is a line. Which means for each v that you take out of here, you get a unique line, and you basically get the same object as long as you're in the same isomorphism class. So this is one aspect to it. And then when you do this, one application is you can use this to decompose bases of automorphic forms. I'll stick to that case just for the sake of simplicity. Let me define L2 cusp Q A. Now I drop the level, I pass to the co-limit over all levels. Omega, where omega is infinitesimal character of V. So just fix one infinitesimal character of one rational representation. And I just want to look at the cusp forms, the smooth cusp forms, where at infinity I transform like this. And if I start with a cohomological type, for example, this one, then I can define a space with index cohomological type, which is just given as a completion over all cuspidal pi regular algebraic with the property that the cohomological type is T. I sum them up. And I just take the smooth vectors inside the. So if I do this, because of multiplicity 1 for GLN, what I find is that the space of all smooth cusp forms, A omega, is canonically isomorphic to the direct sum over T, where this representation at infinity has the, first of all, I need to assume it's tempered, so it's a tempered cohomological type, which I don't define here, or omega, so which has infinitesimal character omega. And then I take all these spaces L2 cusp. U T. So you get such a decomposition. So why would you want a decomposition like this? One reason is if you want to define rational or integral structures on this space, then it's actually more natural to construct them on each of these summands. Because on each of these summands, you can define them as follows. So you, well, maybe I just quote a theorem first. Due to Hayashi and myself. So there is for tempered T as above, so for tempered cohomological types T, canonical O integral model, just denoted AQ. O or well, AQ lambda, or let's say AQ. AQ lambda, where lambda is the one augmented from omega. So omega is just the infinitesimal character, right? But I want to have basically omega plus pi naught action. I want this to be my lambda. So because this has to be taken into account here. Although we just do it in the rational setting first, and I augmented it. For this cohomologically induced standard module, if 1 over 2 df is invertible, is an O. You need to invert the discriminant and you need to invert 2. Ironically, we need to invert 2 for the reason that for general n, On doesn't have a model. But aside, this is true, and using this, together with this, you can define something like this space, these spaces, but over O. So put 2 cusps Q. Omega T with coefficients in O. What you do is you take our module, which is a locally algebraic module of the corresponding weight. You tensor this, for example, with the cohomology in bottom degree. You're taking basically, here you have to be a bit careful what you take exactly. I'm going to take, I know this is imprecise, I'm going to take cuspidal cohomology, although cuspidal cohomology over O is not a properly defined object. I have to tell you how to define it. Of this orbifold of infinite level. So you take a colimit over all the levels with the corresponding sheaves. V, where V corresponds to T. So V somehow is an element of, and then you take a lattice. There's a lattice that you can choose, and you can actually make this lattice in some way canonical, in such a way that in this degree, actually, you're getting a free module over O of rank 1. And you're taking this guy here in this cohomology. So this looks a bit strange, but there's actually a canonical map from this guy into this guy from before, which is the same space, the classical space. So this map is not injective because you can have some torsion coming from this contribution here. We can show that our model is actually projective. This is crucial. It's somewhat, there's different constructions you can try to construct integral models. And if you, for example, try to construct them with an analog of Zuckerman functors, you run into the problem that you may have infinite torsion, which you don't want to have. And we can show that using an appropriate Bayes and Bernstein theory, localization argument, or proper theory of TDOs over O, we can define a module where we can define, say, it's projective. And we can also show its GK cohomology over O is also projective, which is very important for application. So you have this canonical map, and this actually, the image is actually an O model of this complex space here. And you can normalize it in a canonical way if you like, because you can make it agree. I mean, this somewhat is canonical because you have a canonical map from that space into the complexification. From the complexification, you can go here in a canonical way. O is just, yeah, I didn't make it precise. So what O is basically, you take E sufficiently large such that your locally algebraic representation, or it's sufficient to assume the rational representation underlying V is defined over E. And then you take a localization of the ring of integers in E at this element, for example. Yeah, exactly. So you take the ring of integers inside here, and then you localize here. That's what you do. And then what you actually get is there are some interesting. This so far looks like a formal exercise in some sense, although it's a bit technical to go through all of this. And of course, this is in a certain sense Hecke equivariant. What we can show, what I can show is that if you apply GK cohomology to this guy, you actually get a map back into this cohomology in some sense, because this guy will turn into a line if you apply GK cohomology at this degree. I can show this as a line, and then what you actually get is that so you apply this GK cohomology functor in this degree, but you can play the same game at the top degree. You need to do everything here over O, infinity over O. And you need to take this sheaf locally algebraic representation over O, and you apply this functor to this side here, and you get another O integral structure. On, well, actually on all of the cuspidal cohomology. Interesting part. Coefficients in here. So there's a canonical integral structure, of course, that comes from taking the same thing homologically, because you can, of course, you have a lattice, so you can take the coefficient, the associated sheaf to the lattice. And there are some assumptions on the lattice, which I'm not going to make precise now. But what you need to assume is, in the first place, that you have a scheme theoretic action of G on that object. And the pi naught action is also a scheme theoretic action. And then you can write that down, and you can make sense of this. And then you can show that this gives you, I mean, what you can do is, because you get a line in T naught, so you can make these two agree at degree T naught. But at higher degrees, they will very likely diverge, which basically allows you, if you combine these two integral structures, to define a canonical set of periods for each pi with homological type of pi corresponding to T, where the V was corresponding to T. And so, well, I have 10 minutes. Erase the left-hand side. So this relates to a certain extent to Binyong's talk today in the morning. He showed that there's a canonical rational structure on the GK cohomology. He basically avoided the business by just descending a rational structure that you have here onto the GK cohomology. So this point of view is different. You basically move further down, and you want to have rational structures on pi f and pi infinity at once. And this allows you to have these big rational structures or integral structures on these large spaces. And this then allows you to define those periods. So I make two remarks. One is that if you do this rationally, I can show in certain cases unconditionally, in other cases it's conditional. And using Binyung's work, I can make it actually unconditional in many cases. Is related to special values of alpha, so special L values. So basically morphic periods. Of L functions. So this is one remark. And the second remark is, so Venkatesh conjectured that there should be an action. I mean, in this case, if I would just stick to the case where this is a field, okay. So this formulation will make it precise here. So if you fix P, fix regular algebraic hospital pi on the right-hand side, say of cohomological type T. And let's say inside of T you have something like this. Then you can achieve multiplicity 1 by considering coefficients in this V, because this is locally algebraic representation, which produces a line in bottom degree and top degree. So there should be, so if we consider this here, coefficients in xg, coefficients in V over C, or actually over E or over Q. So now E is a field of definition. This regular algebraic representation pi. And you take the pi f isotypic component. So this should admit canonical action of 1 in the category of motives of pi. So I just abuse notation, so pi should be the motive attached to pi. Actually, of course, on the right-hand side you take Q1, and well, of the exterior power. So this exterior algebra, and this actually should turn this into a free module. Cohomology into a free module. Rank 1. So in that formulation, as I understand it, this x1 is computed using basically the external Hom, which comes from the Betti realization on the category of motives. So you choose as a fiber functor the Betti realization. So this should conjecturally correspond to the Betti realization of the x1 computed internally, the category of motives. So the question is, we have two integral structures. So one integral, or you also get two rational structures if you localize, right? So we have a second rational structure. So there's one rational structure which is topological coming from E, and I constructed a second rational structure coming from these rational considerations on the level of GK modules, which is presumably different. So far-fetched, you could expect that, so does the second, is the second rational structure. Cohomology related to the RAM realization of this exterior algebra, but now computed internally. I1. I don't have any evidence for any such claim, but one way you could try to check something like this is to look at examples on GLN where you have some relation to L values and therefore to the Linnaeus conjecture in bottom and top degree. So the bottom degree is basically the Rankin-Zelbadel function we saw in Bignon's talk. In the top degree, when n is even, you can use the symplectic case, or the Schleicher model case. And then you can ask, well, I mean, you can normalize these cohomology classes in both degrees canonically for pi, and then you can ask how do they compare. So you have two different normalizations. And if you can somehow relate these periods that show up here to this motif, you could expect that it's related to the action that I have, because my proof of the same period relations as in Bignon's talk, but a weaker version of it, just a rational version, just compares these two rational structures actually. So there should be some motivic relation between these different actions, these different rational structures or integral structures, but at the moment that's unclear how this should manifest in detail. I think I'll stop here.